Okay, today starts 3-6, the fundamental theorem of algebra. So far we've learned several important properties about real roots of polynomials, and we've said it a bunch of different ways, but the following statements are equivalent. A real number r, which is just some number, could be 2, 7, 9, doesn't matter, is a root of the polynomial equation p of x equals 0. P of r equals 0. That's another way to say it. In other words, if I plug that number in and I get equal to 0, then it's a root. R is an x-intercept. That's the same thing as being a root. And when you divide the rule for p of x by x minus r, the remainder is 0. So that's what we were doing in the last section. Whenever we divided by that r, whatever it was, then it created a remainder of 0. So those are all ways to say this. So let's write the simplest polynomial with roots -1, 2/3, and 4. In order to do that, we can start by looking back at like this part of it, where it would have been x minus r. And we would know that it would be x minus a -1 would be one of our roots. We're just going backwards. X plus 1. That would be x minus 2/3 is another root. And then the last root would be x minus 4. So if I'm trying to write the simplest polynomial, I could just multiply these all together to come up with that simplest polynomial. So the first thing I'm going to do, I'm going to kind of rearrange the way I write these. I'm going to make this minus 4 and minus 2/3. And I'm going to multiply the first ones out. So x times x is x squared. Then x times -4 is minus 4x. 1 times x is plus 1x. Minus 4x plus 1x gives me minus 3x. And then 1 times -4 is minus 4. So that's these first two multiplied together. Then I can multiply by x minus 2/3. First I'm going to distribute my x to each term. So it's going to give me x to the third minus 3x squared minus 4x. Now I distribute the -2/3 to each. -2/3 times x squared is minus 2/3 x squared. -2/3 times -3 is plus 2x. This is -2/3 times -3x. 3's cancel, negatives become a positive, and it's just 2 times x. And -2/3 times -4 gives me plus 8/3. Combine my like terms here, x to the third. Now doing -3 x squared minus 2/3 x squared, it's going to be easier just to make this 9/3. Then 9 minus 2 is 7, so it would be plus 7/3 x squared minus 2x plus 8/3. That's the simplest form of this polynomial. I want you to try this on your own. Try to do -2, 2, and 4. So now we're going to write this x minus a -2, that's x plus 2, times x minus 2, times x minus 4. Now we start to multiply. We can multiply these two together first. X times x is x squared, times -4 is -4x. Negative 2 times x is negative 2x, so I can combine my negative 4 and negative 2. That becomes negative 6x, and then negative 2 times negative 4 is plus 8. Then I have x plus 2. Distribute my x to each term. That becomes x to the third minus 6x squared, and then minus 8 or plus 8x. And distribute my 2. 2 times x squared, that's plus 2x squared. 2 times negative 6, that's minus 12x. And 2 times 8, that's plus 16. That's x to the third minus 4x squared minus 4x plus 16. And that's my simplest version. And so that's all we have to do for this. Notice that the degree of the functions is the same as the number of zeros. If I looked at this one, it was x to the third. There were 3 zeros. Same with the one before it. 3 zeros. It ended up as x to the third is my highest exponent. This is true for all polynomial functions. However, all of the zeros are not necessarily real zeros. Polynomial functions, like quadratic functions, might have complex zeros that are not real numbers. And that's where the fundamental theorem of algebra comes in. So we might end up with some imaginary numbers here. Last section, we just kind of stopped doing it if we got to the imaginary part. Now we're going to factor it all the way down. Every polynomial function of degree n greater than 1 has at least one zero, where 0 may be a complex number. The corollary to that, to the fundamental theorem of algebra, is that every polynomial function of degree n greater than 1 has exactly n zeros, including all of the multiplicities. So if we start with this x to the fourth minus 3x to the third plus 5x squared minus 27x minus 36 equals 0, we can start by finding, or we're going to find all of the roots, whether they be real, non-real, irrational, rational, or complex. So in order to do this, we're going to start by the same thing we've been doing. We're going to find our rational roots, because we want to get to a point where we're down to either the complexes or something else. So let's find our rational roots. P over Q. There's P. There's nothing in front of here, so Q is 1. That makes it nice. P. Let's look at our factors. What goes into 36? Plus and minus 1. Plus and minus 2. Plus and minus 3. Plus and minus 4. This one's horrible. No 5. Plus and minus 6. Then 9. 12. 18. And 36. And then since Q is 1, these are all my factors because they're all divided by 1. All right, so if that's where I start, now I can start choosing roots. And remember, I told you that you can use Desmos to do that. So we're going to pick Desmos to start. We'll plug our equation in. X to the fourth minus 3x to the third plus 5x squared minus 27x minus 36. Now if I scroll out, I can see that I have two roots on here. Click them. There's one at -1 and one at 4. So we're going to start with -1 and do our synthetic division. Remember though, this is an x to the 4th. So there's going to be 4 roots. That's what the fundamental theorem of algebra taught us. There has to be 4 roots, even though I only see 2. So we're going to start with -1. We'll do our synthetic division. -1, 1, -3, 5, -27, and -36. Draw our line, drop the box down, bring down the 1. -1 times 1 is -1. -3 minus 1 is -4. -1 times -4 is a positive 4. 5 plus 4 is 9. -1 times 9 is -9. -27 minus 9, that's -36. -1 times -36 is a positive 36. -36 plus 36 is 0. Let's backfill. -36, 9x. That's a positive, so it stays plus. -4x squared, and then 1x to the 3rd. Now, since I'm trying to find all my roots, I know that -1 is 1, which means I have 3 more to find. I don't technically have to do this step here because I know what all these are, is my coefficients. I also know that 4 is another one of my roots. So I could start with synthetic division here as well and just go from here. We know that it's a positive 4, so 4 would be my next one, and we'd bring this down. Bring down the 1. 4 times 1 is 4. -4 plus 4 is 0. 4 times 0 is 0. 9 plus 0 is 9. 4 times 9 is 36. I guess this is where my box should have went. I went too far with my line because, well, it ends here. 36, -36 plus 36 is 0. Now my equation is 9. And then x squared. Since it's 0x. Now I can do the quadratic formula because I'm at an x squared. So -b, which is 0. Remember that's a, b, and c. So -b is 0 plus or minus the square root b squared, which is 0, minus 4ac all over 2a, which is 2 times 1, so that's just 2. 0, that just kind of goes away. It's plus or minus the square root. 0 squared is 0. -4 times 1 is -4. Times 9 is -36 over 2. Now, how do we take the square root of a negative? We would break that up. Plus or minus I times 36 over 2. The square root of I is -1. I'm sorry. This is -1. Kind of doing it the opposite here. -1 times 36. Square root of -1 is I. Square root of 36 is 6. So I have plus or minus 6i over 2. 6 divided by 2 is 3. It's plus or minus 3i. Now, I have 2 roots here. I have positive 3i and negative 3i, and then I have 4 and -1. So those are all my roots. X equals 4, -1, and plus and minus 3i. That's how you should write it at the end. That way I know that there are 4 roots, and you know what those all are. All right, guys, we'll get into this more on Monday. Have a good weekend.